Moving on to your next similarity theorems, we have side angle side similarity and side 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 similarity. So the first one, side angle side, states if an angle of one triangle is congruent to an angle of the second triangle, and the sides that include the two angles are proportional, then the triangle is similar. So it's very important to understand that it is the sides that create the angle that we're looking at is what we're comparing as proportional. So for this small triangle, side AB should be proportional to QR, and side AC should be proportional to QS. And if both angles are the same, we can state they're similar. Side-side-side similarity states if the corresponding sides of two triangles are proportional, then the triangles are considered similar. And that's pretty straightforward. If we compare the two sides and they are similar to the other two sides and the other two sides, then we can say the triangle is similar. So here is a question. Are the triangles similar? If so, write a similarity statement. So we are given information about all the sides and we just want to compare it. The first thing you want to do is match up the sides with each other. Now this triangle looks like a right angle, but there is no information to tell us it's a right angle. So we can only do our best kind of guess to see which sides match. It looks like SU is like the longest side of the triangle and the small one, and WX is the longest side of the big triangle. So I would say that those two match. So use the side lengths to identify corresponding, then set up ratios for each pair of corresponding sides. So in this example, they kind of like re-highlighted to see which sides were corresponding, and then they're going to set up the ratios. The shortest side is ST and XV, and that's 6. They put the small triangle on top measurement over the large. If you're going to do the number of the small triangle on top and the number of the large on bottom, you need to be consistent. Okay, so that means every time you create a ratio, the small triangle goes on top, and then the large one will go on the bottom. You have to stay consistent with your ratios in order for this to be solved correctly. They reduced this. They look like they divided by 3 on both the top and the bottom. And this is my messy handwriting trying to show division of 3 on both the top and bottom. Okay, so they divided by 3. Ooh, this is messy, messy handwriting. Okay, moving on. And so once they divided by 3, you got 2/3 here. They did the longest side. Looks like they're divided here by 5. 10 divided by 5 is 2. 15 divided by 5 is 3. And then, let's see, the remaining side is 8/12. Again, they're doing the small triangle on top, the small measurement on top of the small triangle, and the larger measurement on bottom of the large triangle. So 8/12 looks like they divided 4 out of both the numerator and the denominator, and so it reduced to 2/3. As you see, looks like every side, when you put them in ratios, when you're comparing the two, all reduced to 2/3. So that's what you're looking for in order to state that they are similar by the SSS theorem. So these two triangles are similar because all their proportions, all their sides reduce to the same number. So that is a key to remember, the same number. Are the triangles similar? If so, write a similarity statement for the triangles. So here we have two triangles that are overlapping each other. This is really hard to see, so it is highly suggested that you separate them into 2 separate triangles. So here it says, how can you make it easier to identify corresponding sides and angles? Sketch and label the 2 separate sides. So that's what they did. So the smaller one is the 8 and 12, And then the larger one is actually the 8 plus 2, which is 10, and then the 12 plus 3 for the larger side, which is 15. And they both share the same angle as K. So angle K is congruent. And when they compared KL, which is the smaller triangle, over the larger triangle, and they compared it, put it in a ratio, it reduced to 4/5. And then when they did, again, another side of the smaller over the larger, it also reduced to 4/5. So we can conclude that these two triangles are similar based on the SAS theorem. Okay, here are two for you to try on your own. Please pause the video and try these two on your own. And then once you're done, go ahead and press play and see what answers you get. Please pause now and go ahead and try these on your own. Okay, if you try them on your own, you would find that the answers are for A, the ratios of each of the three correspond, and the sides are 3:4. So therefore, the two triangles are considered similar by the side similarity theorem. So when you set up a ratio for the small and the small and large, and you did it 6/8, and then 6/8, and then 9/12. Looks like I see 6, 6, and 8, 8. Looks like two isosceles triangles, but when you did that, 6/8, that reduced to 3/4 because they divided 2 out of both the top and bottom. And then this was also 6/8, so another 3/4. And then the 9/12. Again, you got to be consistent. If you're going to do the length of the small triangle on top, then you have to do it always on top. And 9/12, that reduces, it looks like you can take a 3. You can divide a 3 out of both 9 and 12, and you get 3/4. So all sides were 3/4. I'm only showing two sides, me comparing two sides, because one of these is actually duplicate. You're going to have 6/8, 6/8, so it's 3/4 twice. So this is similar based on side. And then problem B, we know that both triangles, if you separated them into two separate triangles, they both shared angle A, and that was the same. And then when you compared the side length AW over AE and AL over AC, small over large, they reduced to 1/2 on both of these when comparing ratios. So we can say that these triangles, these two in B, are similar based on side angle side.